Okay, dann starten wir mal. Also, ich starte schon mal das Streaming. Hallo allerseits. Ich starte nur nebenbei auch die Präsentation, so dass ich nachher einen Pointer habe. Das heißt, 5 Minuten dauert es noch, bis es wirklich losgeht. Remote. Ja, passt, wir starten am Ende. Das machen wir mal nicht. Na, das werden wir auch noch schnell ändern. Herbert erinnert mich gerade, dass ich auch im Discord bin. Das heißt, da gehe ich raus. Da freue ich mich, wenn andere später dazukommen. Und jetzt geht's los. Ja, hallo allerseits. Jörg Simon wieder hier zum nächsten Teil an Vortrag für Deep Learning Graz für das Meetup. Ich finde es super, dass wieder doch einige Zuschauer dabei sind. Ja, was ist das Thema heute? Ich muss diese, warte mal, was er das kommt. So, in der Hoffnung, dass wir jetzt auf Twitch, ich muss das nur noch mal kontrollieren, ob man da jetzt mich und so sieht. Ja, passt, gut. Okay. Jetzt höre ich mich selbst. Okay. Was ist das Thema heute? Das Thema ist Interpretability of Time Series Analysis with Deep Learning, Overview und Tutorial. Und ich habe jetzt noch ein Part 1 dazu gemacht, weil das Thema einfach so lang und so groß ist, dass es quasi unmöglich ist, alles in dieser einen Einheit durchzugehen. Ich habe gerade eine Info am Twitch und deswegen werden wir das einfach in mehreren Teilen machen. Any chance of having this in English? Yeah, no problem. Is everyone fine with English? So is someone not fine if I do it in English? Then it's fine. So I prepared the slides in English anyway, but I could also talk in English. Noch einmal auf Deutsch. Wenn es für irgendjemand ein Problem ist, dass man das wenn es für alle kein Problem ist, dass wir es auf Englisch machen, können wir es gerne auch auf Englisch machen. Aber bitte dazu, wenn vielleicht 1, 2 Leute im Twitch-Chat schreiben würden, dass das passt. Sonst mache ich einfach in Englisch weiter. So, I just said that would be cool if someone English is okay, English is fine, perfect, okay. Okay, then let's switch to English. I prepared the slides in English anyway. So this is the second talk on interpretability I do, and this time it's for time series analysis. And I added part 1 because there will be more than one talk on that because it's just such a large topic. So about me, let's recap from the last time. I'm a PhD student who is using deep learning to detect human factors from biosignals. My PhD is supervised by Eduardo Wes and Herbert Danzinger, who is also the main host of Deep Learning Graz, and thanks for the invite again. So why I'm interested in interpretability, I sometimes have their very sparse data, so I'm very in doubt that all the models we train actually are really right. It's kind of a debugging or making a verification tool for me. Also, I'm inspired to use interpretability results to change the training process itself. There will be some additional talks on that too. Pathway learning is one thing. Remix is another, which we will probably talk, and deep feature, but I will go into that later. I start with some resources, and the most important one is there is this GitHub repository from Graz AI. And some of you might directly want to check out the notebook. There's an environment YAML and so on here, so you can actually get everything to running while I actually first go over the theory if you want. And there's some other resources, and there's also a PDF of the presentation already in that repo. So if you want to easily open these links, then you can just do this by using the PDF and go there. Let's start with a small recap of the last interpretability part. In the last interpretability, we talked about general feed-forward neural network or convolutional neural network, mainly convolutional neural networks. We said that if you have, for instance, an image as an input, then we can actually activate by back propagation or other like layer relevance propagation and other rules. We can detect on which parts a network looks inside of the image to come to a specific decision. But only looking at which parts they look does tell you only part of the story because you don't know what it is actually looking for, which would give you a hint for if there's another image, if it somehow makes sense. So we can also, this is called the max activation framework, look what are typical kind of templates a layer, a neuron, or a path towards the end is looking for. So we can do this for an individual neuron, for a layer or a path, and then actually come to like these template images for this small batch or for this neuron, it would look for something like that. Between each layer of a neural network, there is a set of weights, and what we can do with an image is we can convolve over the image if it's a convolutional neural network, because this is usually a filter, and generate the resulting image after the convolution, so the applied filter, and visualize really what's the output or what's kind of the image for that, the feature image for that layer. They shrink in size, so in the end this is super abstract, so you don't understand a lot anymore, but at least at the beginning layer it's relatively easy. For the last layers you probably need to do something like sampling. Don't forget there is some nonlinearity, we will also have this today, so some of these images will always be additionally changed besides just applying the filter. So this is what we kind of went through last time, and then I had some notebooks where these techniques were explained. And if you're interested in that, again, please just open the notebook of the last time and play around with it. It's kind of, I hope, fun for you and would be cool to do. But today okay, cool. Yeah, there's a YouTube link as well. So you can also watch, last time I did it in German, but you can also watch the talk of last time in German on YouTube. Generally there is a channel for Graz AI. I also uploaded it to my own channel, but look at the Grazia channel, they have more videos because the ones on my are only the few videos I have. Okay, maybe Herbert, you can also post the link in the chat from the last to the YouTube channel. So today's talk, time series. So what is that? A time series could be, I'll start with some examples. Could be, for instance, an audio, a waveform, or a spectrogram. This is from a violin, like frequencies over time pins. So that's usually in reality some array of numbers with a fixed sampling frequency and the starting point. What else could it be? It could be a video. And in reality, a video is nothing else but a set of images and at specific time points. So these are usually then 4D tensors in the dimensions of timestamps, color channels, width, height. Really, it depends a lot on the framework in which order these things should be. It could be stock data. So these are usually then time-stamped events. And for instance, here in stock data, it's not necessarily that way, but we can actually have time series where the time itself is not uniformly distributed. So let me see if I can go here to that again. So if we like look here, these are 1 minute apart and these are 3 minutes apart and 1 minute again. So the timestamps are not even distributed. So it looks like it's regularly in the data, but if you, for instance, visualize it, you will see it's not, and you should take care of that. It could be like telemetry data from a car, like throttle or pedal. So these are then usually similar to audio or stock data, but just with many channels. It could be also speech, which is more or less audio data, but with the assumed structure. And it can also be, for instance, text. And there we also kind of see text is not really a time series per se anymore, but a sequence data. And I would say that deep learning models are actually just sequences. And time series is like one of the most popular sequence. So there can be many more things, but I think you got the idea that these all are usually matrices with values where one of the dimensions is time, or tensors. So what do we do in time series? What's the unit of analysis? So one of the things we do in time series is we want to predict data from the future. So the next word in an unfinished sentence, stocks going up or down, steering angle of a car, that's prediction. The other thing we want to do is we want to classify it. So this is, for instance, an example from my master thesis where I did gesture analysis. You have a stream of several sensors and some time area within this stream is a gesture, and you want to identify is this part a gesture or not. You can also say like the sentiment in a sentence or emotion encoded within an ECG signal or whatever. So now we know what we can do with the models, but what do they really do on time series? I think in all domains with all data we have time series models usually try to do a transition from to a new event given current events. In like classical machine learning, one of the most classical things is a hidden Markov model or Markov models, which actually really model transition probabilities. In deep learning, most time series models actually kind of got to the idea of gates. These are usually sigmoids or softmax, groups of softmaxes or sigmoids, who actually kind of influence the probability that the event is kind of more used for morphing into the next event. all models which do time series analysis do that. That's our LSTMs, wavenets, transformers, or so. They all use somehow these gates who kind of control how this morphing is happening. And we said they want to transition to new events given current events. And now the question is, what is an event? So what I very often see in time series models, and I think everyone who looks at it sees it, that at the beginning, very many people kind of look at individual data points, and then the models don't scale or don't make sense. So an example where it's done better would be natural language processing. There they actually found that not single characters, even if some nice work is done with characters only, are a good event, but like whole words are events, and then they learn embeddings out of that, which are specific representation used for a neural network to work with, which more or less represent already a semantic, even if it's a vector, a semantic representation of words, which you can work with and which you can actually analyze on its own. We will do it a little bit today, and we'll probably go into that a bit the next time. Which is harder is general sensor data, because this is where often people really take single points. And this is very often not such a good idea, because this includes all the noise. This may be not distinguishable by real events. So classical solution in to for instance, remove or reduce the noise is either feature transformation in classical machine learning with sliding windows. So this is actually an important step. Very often they might overlap or not, but to get these things working. And in deep learning, embeddings and encoders very often play a similar role. There are things like wavenets who kind of, or convolutions who kind of have this built in. So we have basically two units of analysis. We have the semantics of the encodings of the events we can analyze, which we will more do in the next part. And then we have the influence of the past events for predicting new events, which we will do today and in many other parts, because there are so many models to do that. Which brings me to the next thing, models. So the interpretability methods I will talk about at the moment are for deep learning, and they're model dependent. So there are things like LIME or whatever. This is not for time series, but there are many model independent analysis tools. But I really look at things which are specific for deep learning, and also I think then bring you maybe some other good insights. And they're all model dependent. So for each model you have other method. If anyone ever took a deeper look into, for instance, layer-wise relevance propagation, and I hope that my friend and colleague Ilir, who also does a PhD on deep learning interpretability, we just recently implemented layer-wise relevance propagation, or mainly he did, for PyTorch, again natively. They have very different rules for different kind of, like if it's a convolution, a linear layer, or a LSTM or whatever. And so this is even within this class of deep learning, very dependent on the different models. So what models are there? Let's see if I got any questions right now. So one of the classical, I should have written that out, but we will in a few slides later. I do. Classical models are recursive, recurrent. Now we have it. Recurrent neural networks. With the most famous, I guess, is the long short-term memory recurrent neural network, or the gated recurrent unit, the GRUs. The image I have here is about an LSTM. So this is a model with which you can actually model this transition, or actually the morphing of past events to new events. I actually bring up, oh, I messed up this a bit, but I bring up autoencoders because they're also a really good way to work with time series data. You can slide them over and they give you quite some info. A really cool other thing you can model, use as a deep learning model to analyze time series are temporal convolutional networks, TCNs. And there is a specific version of the temporal convolutional network where they say a lot, this has causality and whatever in there. This is the WaveNet. And this is actually, I already told a bit, that gates are very important for time series analysis in deep learning. And this is a more or less non-overlapping gated convolutions in a specific form, which a large receptive field in the past. And this works quite well. The thing which works best in natural language processing in this kind of sequence at the moment are transformers. And transformers are really good in autoregressive tasks and denoising. So I think Jan LeCun once said that you can see transformers just as a special case of denoising autoregressive models. And they again use this idea of, they use attention mechanism and multi-head attention, which again are gates with a softmax and not a sigmoid. So kind of, you still kind of want to really attend to something and not just have a gate for each individual channel. But in the end, and they kind of, in the self-attention, kind of lose the temporal structure, so you have to encode them somehow into it by itself. But then they have other good aspects, which we will talk in a later part of the series. So these are, we see we have a lot of models, and also and the methods are model dependent. So for today, I will actually focus more on the most classical of all time series models, which are LSTMs. Also, there are hybrids. You can actually mix and match many of these models, and really in practice, this is often done. And one one of the classical problems I said are LSTMs that they actually most of the time just take a single time step. And this includes all the noisy timestamps and use this for transitions. And this is often not a good idea. So one thing is to have like an encoding and a decoding layer, which is similar to an embedding, or for natural language processing, or for like also genome data. So actually these encoders are used to create embeddings, and very often they are actually extra trained with pre-training. Representation learning is a own area which actually goes into that. This is also something I'm interested in quite a lot, and actually applied to some sensor data, so we can actually also look into that. But this is like, to get these encodings well is somehow important. Then it really helps. And we will take, not in representation learning, but how to somehow use them a little bit also today. Just to recap, there are many ways to, like, not time series, but sequence models, but actually all of them are. The one we just ignore, but one-to-many, what is that? Andrew Oenkke gave a good example. You, for instance, want to give one random seed and let it generate music. Then you would have a one-to-many model. Many-to-one, that would be, for instance, classification, or even if it's regression, but like one data, like the emotional value. Many-to-many exist in two versions. One, for instance, the first many-to-many we see, like the second to the left. Let's quickly see if I can. So this many-to-many here, this is usually used for translation. So this is very often done in natural language processing. There are also, like in this many-to-many here, there's usually like the input here and then the input to translate again added as some input to cheat while training a bit, and then just not added on inference. So they look different at training and at execution time, and then you kind of get the output here. So translation is one, and then this is more the autoregressive thing. So usually you have an input and like an output shifted in time one step or so. This is the one thing we will actually look at today. This is like very, like if you work with sensor data, a very, very common model. Let's quickly recap recurrent neural networks, RNNs. So this is like the most basic recurrent neural network. It's like you have an input at a time step and some RNN cell, which produces an output and kind of, but reuses the old events. And in reality, when you train it, you kind of unroll it, and you also see the formulas up here. But I think the most important thing is one thing. So you have this weight matrix here, this W, and the input matrix U and the output matrix V, and especially the W. And this is, I think, what many people don't get too much. Don't get too much is, so this weight matrix over all time steps is the same. So many people kind of think like we have a weight matrix here and the weight matrix here and one here, and this is not true. We have one. We have exactly one matrix which encodes the, for instance, in case of a LSTM, several things. It encodes how much I am likely to keep my old cell state, how much I'm likely to keep my last state, and how I transform that into a new hidden state, which is actually really a transformation of the features. But it's like one thing. And while training, this means that all the gradients are kind of averaged over all these things to, in the end, produce just one matrix. This is important because we will use this effect later. And I think it's also important for understanding. So we want to find this one thing which gives us a good morphing. So we will go today look at long, short-term memory, LSTM cells. And for that, let's recap its inner workings. This is actually taken from the cola.github.io posts. This is a really cool set of posts on how to understand neural networks in general. He did a lot of interpretability, and a lot of his work then ended up to go into distill.pub, which is an online journal with a really cool review board on interpretability. And it's some amazing work, and there was always this idea to make deep learning understandable. So beside all this advertisement, let's quickly go into it. So one of the problems, if we look back into this recurrent neural networks, is, as I said, these time steps here, they all, like on training, they get averaged. And like if you like then have a sequence where you want to learn this one weight, but we have all the influence from HD to X0, and this is already quite a time chain, a longer one, then we actually have to multiply usually with a number, because they all use, usually they use Dunn-H, but like with an LSTM, they're for instance some sigmoids, or so these numbers are usually below 1 or 1 to -1, and then we use some fraction number which kind of makes it smaller and smaller. With the weights, you can also have it explode, but then you have exactly the contrary, it's going up and up, so that the gradients totally play havoc. This is actually we have the same thing in skip connections and residual connections in convolutional neural networks. And the same thing is here in the LSTM. You want to have some way where it's easy for a gradient to survive. In case of convolutional neural networks, the residuals let you survive the many deep layers of the convolutional neural networks. And the LSTM has the cell state. This is what in LSTM it's called, or the long-term memory. And this is actually something which is not as easy to change as this weight matrix W here, which kind of really always changes a lot. This is the idea. So we want to have two states, the cell state and the hidden state. Both are actually kind of taken from the past event and propagated in the future, but one should be a little bit less brittle to change than the other one. How do we do that? We do that with what they call a forget gate. If you look into the math, what it really means, it's actually more a remember gate. So you always get the input of the last layer or your input and the last timestamp. And you kind of really, on the size of the hidden, you really just, usually you you add them actually. It depends a little bit how you define that. You can either have two matrices and add them, or you have one matrix who does it for you. In PyTorch, it's actually that way that there are two matrices. Anyway, you kind of take these two things, concatenate them, or concatenate them and have one matrix, or you have two matrices and add the result, and then you add a sigmoid over it. And this means like your last time point, your last hidden state, and your current time point kind of determines how much of the cell state will be kept in future, because the sigmoid numbers are obviously between zeros and ones. If they're zero, you forget that part. And since you always add your new event, this means you completely forget it, but still you have your new morphed input added to the cell state. Or if it's one, you just ignore whatever new comes. No, you don't do that. You just take all the old time. Here, you still kind of morph it because you will still add the new information. This still kind of morphing is the next thing. This is the input gate. The input gate actually, again, does something very similar. The first thing looks pretty much like the forget gate. And then it kind of gives you, given that a done age, an additional, like this would be now really the morphing, like the content-wise, the features. And here we kind of learn separately how much of this feature we keep. So the gated recurrent unit, for instance, the only difference is that they kind of couple this IT and FT. And then this is computed as feature, and then they both are multiplied, so that IT is, again, as I said, these are all gates. This is the whole idea which are used in time series all of the time. Gates who selectively then say, yeah, we transform a new feature, but only that part. We learn that only in this, for time steps, only that part should propagate the truth. We then actually, the first thing is here we say to come to the new cell state, we say how much of the last cell state we keep, and we add new information, and this is our new cell state. And then we compute a sigmoid over, again, over the input and the last time, like another gate, and then but then use the cell state to produce the new hidden state and the output. It's the same. So the new hidden state in time and the output to the next layer. That's an LSTM. Okay, this information is a bit important for the next steps, because now we will actually move to the notebook I prepared, and I even have for myself, I had some cheat infos, because before we move to the notebook, and let's close the presentation for now. I hope so far everything was understandable. Okay. So, yeah, here we are. This is kind of seeing myself. Now I wanted to start first. Okay. So when you go and look what LSTMs do, a lot is actually just influenced by this paper, Visualizing and Understanding Recurrent Networks, from Andrew Caparti, Justin Johnson, and Fei-Fei Li. If you ever did the YouTube Stanford Vision class, you will know all of them. Andrew Caparti is obviously now at Tesla, but Justin Johnson and Fei-Fei Li are still there. And what they actually did is, for text, they actually took the source code of the Linux kernel and learned character level RNNs, LSTMs and different things. And for text, they actually then looked in how much one random cell activates really at the output, and colored that positive or negative depending on the activations. So that's what they did. I consciously decided to not replicate that per itself, because I think you can find some things on that online. Especially there is a, like as I said, distill.pub is for, if you're interested in interpretability, one of the coolest things to read. There is a really nice visualizing memorization in RNNs thing, and they already do more than Caparti, because they actually don't really visualize the memorization, they visualize the activation. In reality, they also explain vanishing gradients and so on nicely here. And they actually have this connectivity objective, like, which is the gradients over time, which you can look at there. And this also brought to some ideas the idea of layer-wise relevance propagation for LSTMs. I wanted to implement that, I just didn't have time, honestly, so I will do this in the next part. And there are also some cool prior works, like LSTMvis. The problem with this is it's like updated, like most of it, like quite a few years ago. So if you want to use it for your current system, you either have to use very old frameworks or update it by yourself. It's again mainly done for text, using LSTMs and embeddings, but it's really nice. Like it's for a translation model, sequence to sequence visualization, the one sequence to sequence set which are used for translations. And what you can see there is really cool. You can actually, they use attention mechanisms, so you can actually look on from the things on what the attentions to the embeddings are. You can actually, can I undo that again? Attention. You can look at the embedding state, what is near of it, and then you can actually force it to do different inferences. Like I can change the tree. This takes a while. But if you're in natural language processing, this visualization is really cool and has a, yeah, I want to have the decoder here, and I want to have, let's say, travel. Oh, why doesn't it work? This worked just a bit ago. Let's reload it. So you can play with it. It's a really cool visualization. It probably would need a re-implementation for any current project. So maybe now we can actually. So here now we see the embedding state as I had it in mind. So you kind of have a Disney dimensionality reduction of the individual words, and like now if I here for instance select a different word, then it changes the path. Okay, it doesn't compute. Anyway, I really recommend to check you out. You can over the repo go to the demo, and the link to the LSTM with repo is in the resources of the PDF. But let's go to what I prepared. So I actually prepared a very simple example for time series data for more like sensor-like data. There are 3 notebooks, and we will go through each of them like in the order of simple, simple with noise, and encoding, decoding. So let's start with the first notebook, which is the interpretability of time series, simple sinus. So what do we want to do? We have some classical time series data, and we have it until some certain time, and then we will predict the next time. In this same thing, we will train it in this classical thing that we always have one next input kind of shifted in time. I will actually, since this works really fast, and it should also work for everyone with a CPU. Here it is on a GPU, so I really suggest you check that out. If I restart the kernel, we go through it. So what I first do is like what are we training on? We're training on so the red dots are the input. What I generate here in the first thing is a sine wave, a very simple sine wave. And we want to train the LSTM in a sequence-to-sequence manner. And as I said, like it always should predict the next time point based on the last time point. This is a really, really simple task, but a nice task to train on it. If you have seen a very similar notebook, the Udacity deep learning course uses a almost similar notebook, but I modified it a bit so that you see more of the time series, and especially in the other ones I changed a lot. So we have the standard code to see if we train on the GPU, and then I define call it sinusoid LSTM, but honestly it's really just a standard LSTM. You can use it for whatever problem, which is LSTM and then a linear layer from the hidden state to the output. Why a linear layer? Maybe I quickly explain that. So here we see that the output is of the size of the cell state, which is of the size of half of the hidden state, more or less, or the hidden state. So if I say a LSTM has 8 features as a hidden state, or 265 or so, then for each time step the LSTM itself will give an output of 265 time steps. And we want something else probably, so maybe we want an output of 2 and so on. What we usually then do is for each of the time step just have one fully connected layer on top of it again to produce that. It could also be different, so in encoding, decoding, we will for instance use convolution and deconvolution. The forward is really the standard LSTM, so we just run it through the LSTM. You always get out output and the hidden state. In case of the LSTM, this is important. This is not a tensor, but a list of 2 tensors, the cell state and the hidden state. Out of whatever reason, the output is not in memory formatted nicely. So if you want to change the dimensions, you always have to call this contiguous. You can, if you put that in Google, you immediately come up to an explanation. It's basically the memory layout is wrong. And then you can change it to have all the daters in rows so that the fully connected layer just goes on each time step per each batch sequence. And as I said, the hidden, we have always two hidden, so this is important. We have two hidden states, one for the cell state and one for the more or less classical hidden RNN state. Not really. Did I already execute that one? Let's just re-execute it. It's 4, yeah, it didn't. So we have this LSTM, and now let's say we do our task is really simple. We have sinus, and we shift it in time. So we have one value as the input, which is the current value of the sinus. We have one value as the output. We say we want to add 8 features and 1 layer. You can ignore this warning easily. I think I added dropout, which is used for multi-layer. We use a mean squared error as a loss, obviously, because we have a regression task. We always compare to some floating number and just used Adam and played with the learning rate. So this is wrong. It's this learning rate. This is when you copy things. And then we have a standard training loop, but or not completely standard. What I do in this training loop is actually I always generate batch size times sequence length plus 1 a big sinusoid curve, and then I reshape this whole thing into batches. And actually, so X is then the sinus 1 time step to the last after reshaping it to batch size, and the other one. So this I shape. So for instance, if the sequence length is, I think it's currently 40 or so, then I actually create 41 times, for instance, let's say 2 batches at times series. So we have 82. Then I reshape it to 2 times 41, but then in X it's 2 times 40 with not having the last one, and in Y it's 2 times 40 with ignoring the first one. That's what I do. Then we create a tensor out of it, we run it through the LSTM, and yeah, do the standard optimization and whatever. So if we do this for, let's say, for instance, 300 time steps, and we print it every 20 steps, we use gradient clipping. This you just do with LSTMs so that they don't explode. Then we can see how this evolves. Criterion, I probably did not execute these cells. And then we see, okay, it starts out pretty lame, but in the end it gets better and better. Let's look at the last. Could you please set your browser to full screen mode? Sure. I know there's a shortcut to it, but now I'm not really 100% sure. Enter full screen. Yes. Just saw it a little bit later. So if we then, yeah, that's nice. Run just the last few steps, an additional last few steps of training with, so you get a pretty good LSTM modeling that thing. So far I didn't tell you anything on interpretability. And one more step I don't yet do. First, let's say now when we have trained this model, how do you use it? So for instance, we can prepare another, like an example where we have this many time steps and we want to predict this one. Then we just shape X to be in this one batch, sequence length, one channel form. We put it on the into a tensor on GPU or not, and then we use the LSTM to predict that data. And now we actually, the prediction is now a value for each time step. but we want, for instance, here just the last one, so we just take here predicted -1. And if we look in our model we just trained, it's pretty okay. So it's pretty near from where it should. So what exactly? So this is what we now have. We have a model. We can perform inference on it. We trained it on a sinusoid example. So what can we now do with it? So first of all, we want to actually, for instance, go a bit into the inner workings of this whole thing. And one of the things is you want to get the weights. So this you can do with state dict. Sorry, I will quickly close that. This you can do with the state dict, and there you can actually print. There should be different now the weights we just learned. So these are all the weights, and now the thing is that actually PyTorch kind of makes one big weight out of the individual weights to optimize it. So if we want to get, for instance, the weight for the gate, for the forget gate, or the input gate or so, then it's actually, you have to know that they're in, this is always the important, they're in LSTM weights, input hidden 10, they're really always that way, and then like it's the shape hidden X, and so you wanna like always, and they're stacked on each other, so it's hidden, 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 so you have 0 to 8 for the input, 8 to 16 for the forget, so it's 0 indexed, and we all know in the slices in NumPy always exclude the last one, so it's 0 to excluding 8, 8 to excluding 16. So yeah, so we can kind of get all these matrices out in the form we want. And we have we usually start with a 0 state. And now we can very easily, we have all the weights and all the things, so can very easily redo these gates. So there is a forget gate and the input gate, and they really just are these, the implementation of these formulas. Really nothing more. I actually took this, I documented this here from this nice article, but I modified it a bit if you look at this, if you notice from this article, because in this article they actually have this here as an output, but I'm, for instance, now very soon interested in the gates, like in how much we really let truth in time. So I modified the code to actually give me the gate and the real output of the individual, like this, it's still called gate, but like the whole morphing, let's say that. Because why not? You can always do that. I obviously need to have the same hyperparameters. Now what we can do is actually we can go through the data. So we just said we have this sinusoid data prepared for us for inference before. So this data here, X. And then, where am I? And then we can actually just, instead of compute the LSTM with the LSTM, just use these formulas, because this is a LSTM. LSTM is a forget gate, a input gate, the cell state is the adding of the forget gate and the input gate, and then we have an output gate, which is the output. We just need to have a fully connected layer then on it, and like the other things appended to each other. Like as I said, I always now give the gate itself, the sigmoid activations extra per per gate. And I can actually save that into a list, for instance. So, for instance, we can now, for instance, look at the forget gate in depth with this method. Did I execute all of this? I think, yeah. So let's, for instance, the first gate I saved is the forget gate. Look at that. So what do we have here? We say we have 41 time steps. That's why I iterated with data. I should actually iterate over x. So now we have 40 time steps. And for each time step, I get a matrix of 8 by 8. Because my cell state is 8 is a vector of 8, and I want to get something out which has the dimension of 8. So I keep this thing. And if we look at this, for instance, we can look at the first column and see, or like this is like the whole matrix for the first input of the forget gates. And don't forget, these are not, the weights are always the same, but the forget gate uses the first time step and zeros in that case and adds them together. And that's why these are always different values by time steps. And then like each column kind of is actually the weight for one feature dimension. So we can, for instance, see how much in the time step 1 or whatever time step of the 40. We can also look at the 20 in each of the cells, each of the hidden state keeps. In our case of the sinusoid, most of them are relatively uniform. We do have some variation over the time steps, but that's not what I wanted to do. I wanted to go to time step 4 here. But in general, they are all like around 50. We can also just take the mean over the whole matrix. And then we have 40 timestamps. We see that on average, each timestamp retains about 60%, 50 to 60% of the last time. Don't forget that this is like, it retains that part as a basis for morphing, and then we add the new thing and morph it into a new feature anyway, but still that's it. So in our case, we actually can say it's between 55, so I actually need to modify our new trained model a bit. Let's do 54. And now we can, for instance, visualize our model. Oh, that's interesting, because the one which is checked in will have a different remembering structure, because this is really remembering more of the peak, this model. And my last model was actually remembering more of the start, then went down and then a little bit at the end again. And both are really good models. This model is a little bit better. Yeah, so that's what you can do. So you can actually now visualize this part of like how much of each cell state kind of remembers. I think this is already quite a interesting thing. Yeah, and the last one I will finish that code. I think I wanted to go over make this picture for each of the cell, for each of the 8 feature cells. Let's see if we can quickly do that. That should actually pretty quickly work. Timestamps, and I actually just use it here. So I think that should work, and probably now we need to rescale it, else it looks whatever. So num p mean, and let's just subtract 0.44, no, 0.45. Okay, now we can actually visualize each of the cells for get gate. And we see they're, in this case, relatively similar. Some are pretty strange. I mean, if you look at this blob and blob, so like a dense remembering of the last things, but then individual outliers. Yeah, like if we see that, so it's pretty hard to actually. Did I actually now made 40 out of them? And the visualization doesn't make a axis. I want to have it bear. Forget. Sorry. This was shape 40, yeah, so this is 8, 8, and we want to have it column-wise. That should be axis 1, and it should always give us then, oh yeah, it gives for, that doesn't make sense. Get in the last time step. Now I confused myself. I will fix that and we'll give you 8 nice outputs. Okay, let's quickly change. What else did I prepare for? Okay, so we had this. This is pretty much the same notebook, just less well documented than the other one. So again, you can, I hope, quickly run into it, but there's one big difference. In this case, we actually add noise. So it's our input is this noisy sinuate signal, and our target is this fine one. Just to see what's the effect of there. So the noise is really, really easily done. So it's just numpy random normal with some mu and sigma you define here. You can play with that. We can also add more noise. Let's see how the model trains with that. Then the rest here is for now completely the same. I just still just duplicated the thing because I thought it's easier for showing these things. So now if we train, we see it again starts pretty crappy, even with the noisy data. But it actually, I think, still goes to a relatively nice state, and we can always, like, for instance, execute that cell a bit more if we want to keep it training and see if it gets a bit better. Oh, that looks good. And now we can again say, now I create one random, because like at the first thing you could say it's always the same data, so it's super easy to predict. Now I created a new inference sample with a complete new computation of noise, some random thing. And I can again move that to the as a tensor, do the GPU or so, and make inference. And let's see, is there any? So it actually looks as it got it 100% right. This is surprising. Like as we said, we always have some stochasticity here, and the last model also the one checked in was a little bit more off. This is pure luck and probably will never happen again. If I create another set of noise, I'm pretty sure this will not be as effective. Yeah, here we have a difference. Anything else would have greatly surprised me, but that's with the lottery, huh? Having a really good example. Again, we can do the same here again. We can get the state dict out of it. We can get all the weights. We initialize with 0. We run our own inference now manually. And we can pretty much do the same. Look how the model learned. We actually have more or less this one. And here we now see how it kind of how much per each time point it used the cell state. So I visualize it that way, that I still kind of take each time point, but then I make it on the size how much of the last time point's cell state info is kept. And this is the average over all time points. So obviously we could also compute here something different for instance, f numpy mean for f. Let's take, for instance, the thing for the first column, more or less, like the first, yeah, so this is now the first cell. And here we have what the first cell is. And now we can kind of search if we find any interesting cells. Okay, so we can do that. So this is actually just that to make. I wanted to start with the easiest example first, but to make it a bit more realistic. I think you never have non-noisy data, but we see that the LSTM still captures this really well. Okay. So, but as I said, we don't seldom we have a problem with the events, because now we have actually noisy. We take each noise timestamp. The bigger the dot, the more you remembered from the previous state. Exactly. This is exactly the visualization I did. So I kind of, so, and the more it remembered from the previous cell state, so from the long-term memory. We could also visualize the short-term memory. Maybe let's go back to the other one, and this is with noise. Yeah, let's quickly do that. So as I said, like in this inference, I kind of that forget gate, input gate, and hidden gate. And if we count here 0, 1, 2, 3, that's really hard. So then I'll just for now say this is like the hidden gate, or let's yeah, at least do that. So it should be, everything should be the same. Don't want to change too much of that code. Then usually I would say that usually we just see more variance here. In this case we don't. That's interesting. But as I said, we know like these models are like stochastic in nature. So what I kind of do is like some normalization here. No, that's HM. Else, yeah, that's better. And so this would be so it's, you have to play also with the scaling. I did it now by hand with some brute force heuristic. But like if we could find a better scaling, I think we see it a little bit that, for instance, the cell state kind of more has some like over the whole, if you go through the whole time series, remembers a lot at the beginning, then kind of goes a little bit less, and then a lot in the end, which is, and the hidden one actually does it different. It remembers less in the end, more in the middle, and then less in the end again. But it depends a bit on the model, how it's trained. So this can be very different on very different runs on models. So this is also shows you that it's very brittle to the most important hyperparameter, the random seed. So you can actually probably play with that to go to a good model. But yeah. Okay, let's actually start with the notebook, which should give an outlook into also, I hope, the next part of the series. The simple RNN, the LSTM with sinus and some encoding decoding architecture. We have the same problem again. Let's go with the 3 or yeah. It's more fun. But here now actually we have a different LSTM. We have the LSTM, but we first start with the encoding layer, which is a 1D convolution going over the input sides, and the decoding layer. And I did it that way that actually the stride and the kernel size is the same, so there is no overlap. So you can actually see the encoding really as something as an embedding. I still call it encoding because we also need this decoding, which is a deconvolution or conv transpose 1D thing, which expands in size again with learned weights. This is really messed up when it goes to in PyTorch to the dimensions, because 1D convolutions want to have the format batch size channel time. LSTM wants to have batch size time channel. And usually most optimizers want to have batch size times time channel, so we still use that for the fully connection. But then, or for the fully connection to easily work, but then we actually want to go back and then use the deconvolution, which again wants to have batch size channel time. And then we want to give it in that format for the optimizer out again. So this means that we actually call numpy few like pretty much all the time. And if you want to be interested how this progresses, you can change these debug shapes to true. It will give you a lot of print output while training, but it's probably worth looking at once because this is a thing you can easily get wrong. So what I actually now create is LSTM with an encoding with a conf1do with a kernel size of 10 and a stride of 10. So as we see here, so currently I think it's at the very beginning, the sequence length is 40. So I actually encode the sinus into 4 chunks or 4 embeddings. And I actually, so this is one sequence, it always goes up and down, so it always iteratively trains on one going up and one going down. So we have like one embedding for this and for this, and then for instance one embedding for this peak and for this peak and so on. So that's what we just made. So we have a conf1d to learn this embedding. We have LSTM. We still need after the LSTM the linear layer to get it. We wouldn't actually need that one. I will probably try it without the one. But then we need the conf transpose to get it back to the input size we had. We still have mean squared error loss. And the important thing is now we actually reduce the number of timestamps in reality. So maybe I'll switch that on once at training, and then we just retrain. So if we now train, as I said, we should, did I probably just switch it on, but not, oh yeah, so for instance, in our case, we say we have 4 batches of sequence length of 40 with 1 dimension. And then we switch that, but then we do the convolutions or the embeddings, which actually creates 4 batches of 8 timestamps with a dimension, with 4 dimensions. That's how I defined the hyperparameters. So now the LSTM has way less temporal time to learn. And some of the noise encoding can actually, and decoding, some of the noise things can already be captured in the encoding. And this is the whole idea. And it's probably easier for the time morphing. Let's do that to false again. So here we see the whole thing starts out pretty bad in that case. But now we also see that there are sections of like embeddings who don't seem to work, but sections of embeddings who seem to actually start to train correctly. This is actually really bad. I had a way better model the last few times. I guess I increased the noise, and so this models kind of seems to need longer to train. Okay, this is random seed, huh? Let's just restart everything. I don't need to restart here, but let's recreate the LSTM and hope we get a bit better model. Did I change any hyperparameter? I'm not too much aware. Ah, wow, that's quite some change. So we now see, we still see this. So these are embedding. So we have bare curve 4, and out of whatever reason, the first time these embeddings probably collapsed everything more or less to something a little bit below 0 pairwise, and 2 started to work. And then out of whatever reason, the embeddings itself kind of started to work, and then the whole LSTM kind of starts to model it nicely and the gradients begin to flow. So I guess if we run that the second time, we should get an even finer model. But again, we now see that there's a huge influence on the embedding itself. So it learned that there is actually always some difference in the noise, and you can actually investigate and correct that. Again, let's do one example of noise and inference just to see how this is working. And this model is a bit more about in this case. This is not always the thing. It depends a bit on how you train it. And like after you trained it, we can do now something. We can actually try to gather these embeddings. What do I do this? I do make one large data set, relatively large, of 100 times pi. And run it through my model. And actually, I didn't say that, but I did also here. This is something I can do in PyTorch always, which is nice. After running the encoding, I actually copied and detached it, this one embedding, and saved it in embeddings and returned that as an additional thing. Usually you only return out and hidden. I also return embeddings, why not? And here in the, not in the training, in this large data set inference, I actually, when I run the LSTM, I also get all these embeddings out. I think I just executed that, yeah. So they have these shapes, and now you can do different things. First, you could actually, if you transpose them so that one kind of embedding is one row with a delimiter of t, save them. And then you have this DSV file here. You can download it. I already did that. And there's a wonderful TensorFlow projector site, which is just there for you to play with embeddings. We have new embeddings, so maybe let's download them again. Embeddings to DSV. You load them here. You choose your file. Upload them. Open it. And we have our new embeddings. We, for instance, chosen PCA, and it shows you that you have 4 clusters. Maybe you want to have, for instance, UMAP with 4 clusters again. And then you could, for instance, here try to see for these embeddings if there are some indexes near each other and can visualize that. I also prepared relatively towards the end some code to make this also directly in a notebook with a Disney. I'm actually pretty sure it's pronounced Disney according to the original author. Others with Disney visualization. And also here, oh, that's interesting. So you always have a very different embedding space. It depends a bit on the training. Also here you have, let's say still 4 modes, but they're pairwise very similar. I think we saw an interesting effect in the training here also. So that they were pairwise very similar at the beginning, so maybe something happened there in training. As I said, this is always very different whenever you run it. So what I did with the run before is I actually went to this is totally stupid, but that's the way in time which I could prepare it. I went here and actually looked at some indexes and kind of got them out and by hand by taking the index numbers times 10, because we have a stride of 10 and a filter side of quantum embeddings. Oh, that's cool. The filter size is 10, so the index there times 10 should give you the index in the data. And looked at how it looks, and obviously we have an up peak and down peak part. As I said, we have 4 things, but it goes up and down. So we have for instance, one embedding which looks at this, but it looks at this at the same time. And from the Y thing, this is also from the labels, this seemed to be embedding for that. And if we look at the data, this was with a mu of 2, but it's still noisy and in the negative part. And if we then look at the features it learned, this is not directly, but some features seem to actually retain some of the data because they're negative and they're negative too. And with a Relo, it wants to get some positive value to retain. And they are relatively near of each other, and they probably somehow collapse the noise. But then there are some features which are there to remove points, because they're positive with something negative, and with the Relo it will vanish with another similar embedding. So that's what you can do. You can actually do a lot more with embeddings. So there are things like debiasing or even changing or correcting model. You can somehow even inject informations. Like this classical example is from natural language processing, where you would actually look and if you want to, for instance, debias something, look at these man-woman words which are associated with them, then try to find the plane in the embedding space mainly associated, and you say that's the gender plane, and then you can use it to debias gender things, because they found out that, for instance, if someone works in a house, it kind of assumes you're a wife, and then you can actually inject this knowledge into the embedding space by debiasing. We could do, for instance, something similar here with, for instance, trying to find these, get all these, this is the fourth embeddings, pretty sure. So we can always try to find the fourth embedding and see that it has a different noise and correct it by hand. This is something which is pretty hard to do with LSTM alone, because it's hard to understand this, but this is like a single matrix which you can geometrically interpret, and you can correct, for instance, this angle if you want. You could play with that. How to do that, I hope I show you next time, because that's what I prepared for today. I hope that was more or less somehow nice still for you. And yeah, so that's to sum up. With LSTMs, what we can actually very easily do is get the gates and look on how much to remember in the past. There are some more, some different approaches to see that. This is just like how much the gate says I remember or use. But then you also want, for instance, to see how much the total influence of this feature is, or so then you would use layer-wise relevance propagation, or so we will look into that. I hope that the next talk is by Ilya and maybe me. I asked him and he said he probably does it on layer-wise relevance propagation itself, because this is a very useful technique for interpretability. I will do a talk on finishing the LSTM with these embedding things and LRP. And then we saw that there are many other time series options, convolutions and time, for instance, the temporal convolution network, the WaveNet, the transformers, attentions. Because of that, it was so much, it would never work in an overview even there. So we will do a set of additional things. And I always look for if someone else also does something. Remix and deep features and pathway learning as things I also work, which are hopefully papers in the future. Yeah, thanks for the attention. We will continue with a question and answering in Discord, and we will post the link in the Twitch chat. And that was it for my today's talk on time series interpretability. I hope you liked it.